Okay, hello. Today I am all by myself. And I think I'm having a bit of difficulty with the volume settings here. Well, okay, then I'll probably turn this off. Okay, so let me start quickly. I'm trying to, so we'll do today so we look at the last chapter from Landau's first book on mechanics, and this section 40. So this chapter is about canonical equations. So we look at different formulations of equations of mechanics. And so let's start. So it starts with the Hamilton's equation. The motivation behind this is that whatever we've done so far is a description of the mechanical system will be given in terms of the coordinate and the velocity of the different parts of the system. But sometimes it turns out it's better to describe the system in terms of its position and momentum, where this momentum is the canonical momentum that we defined in our Lagrangian mechanics. So if you're given a description in terms of the position and momentum, the question we ask is, can you come up with a set of equations which use x and p instead of x and v, or x and x naught? So in order to do this, there are mathematically the word is called, there's a word Legendre transformation, which means which is a means of going from one coordinate or one set of independent variables to another set of independent variables. And so let's see how it works in this case. Recall, well, not recall, you can actually write the Lagrangian dl as del L by del Q dq plus del L by del Q dot dq dot, where dq and dq dot represent the independent variables qi and qi dot, the infinitesimal change in these. Now recall that pi by definition was del by del Q dot, and del L by del Q is pi dot, and this follows from the Lagrange equations earlier. So now if you plug these in, you get dl equal to summation pi dot dqi plus pi dqi dot. Also recall that you can write this as a total derivative and subtract off another term, in which case when you make the substitution here, you would effectively get an equation, pull out L, subtract pi qi dot. Well, in this case, we're doing it in the other way. So you're subtracting L from pi qi dot, and whatever's left goes on the other side. And this equation is very interesting because this object in the bracket actually is the energy of the system. Oops, sorry for this. Okay, so this term in the bracket is actually the energy of the system as pq dot minus L. This we had derived earlier by looking at the time translation invariance, which is conserved. So this is the quantity that one gets. And when this quantity h is expressed in terms of position and momentum, this is called the Hamiltonian of the system. Okay, and if I substitute for this expression h, I would get dh equal to minus pi dot dqi plus qi dpi. Now look at the independent variables in this equation. Independent variables are qi and pi, and so therefore you can actually, being a function of q and p alone, and if you think of, and it would then follow that del h by del qi is equal to minus pi from this, and del h by del qi dot would be qi dot. Okay, and these differentials are called, these differential equations are called Hamilton's equations. Now there are two interesting things to be said about these. One is the fact that we have now two 2s first order differential equations which solve 2s. You have to solve for 2s unknowns, p's, 2s, SP's and SQ's, and compare this to s second order differential equations that are obtained using the Lagrangian method. Okay, so that is one thing. And the other part is that these are also called canonical equations because these have an evident symmetry in Q and P. And yeah, okay, that's it. I think I made a mistake. It should be del H by del P here and not Q dot. So that's my mistake. So del H by del Q is Pi dot and del H by del P is Qi dot. Of course, there's a minus sign difference. Okay, so okay, now one thing which we would like to add a little later is time dependence. We did not add any explicit time dependence, as you can see in this expression for dl. There was no explicit time. We'll come back to it in a moment. But before that, let me say that if I write the complete time derivative of h, it would have del h by del t term and these two other terms. What's interesting is that if you make the substitutions for del h by del qi dot using the Hamilton's equations, so you'll get a minus pi dot, so you'll get a minus pi dot qi dot, and del h by del pi is just qi dot. Okay, so you would have minus pi dot qi dot plus qi dot pi dot, and so it of h is going to be del h by del t. It would only depend on the explicit time dependence, and if there isn't any explicit time dependence, then the Hamiltonian, which is basically the expression for energy, that will be conserved as a function of time. Okay, now getting back to the question of having an explicit parameter, explicit time dependence. So what we'll do is we'll assume that there's some general parameter, addition parameter lambda, which could encode, for instance, an external field or some force, which doesn't, I mean, some explicit external force, which depends on time, and so on, into the Lagrangian. So in that case, I would have to write my Lagrangian, the variation in my Lagrangian dl as these two terms which we had initially, and in addition to that, we'd have to add a del L by del lambda d lambda term. And if we use this equation to start with, instead of the equation we started with this, okay, then over here, at this step, we would have a minus del lambda by, oh, so del L by del lambda term, right? Because it would be a plus on this side, and you take it to the other side, it'll become a minus. So the equation for dH in that consequently would become minus del L by del lambda d lambda. Okay, and then of course you can just read off del H by del lambda, holding P and Q constant, because you see P and Q are the independent variables, has to be equal to minus del L by del lambda, holding Q and Q dot constant, because Q and Q dot are the independent variables. Now, of course, lambda was assumed to be any general parameter on which the Lagrangian depends. It could even be explicitly the time. And if there is an explicit time dependence, then del H by del T would be given minus del L by del T. Okay. And that's all I did for today, and we'll see more later.